is in ICTP in Trieste, in sabbatical position. And he's going to talk about LASS2015 correspondence.
First, I want to thank the organizers and everybody. So it's great to be here. I'm very tired. You probably know this, so you'll have to bear with me a little bit. But I'll do my best. So the best way is to ask me questions and to stay interactive. And that way, now I appreciate people as well. Okay, there you go. So. I don't have any, I have some notes, so I want to talk about the literature first of all. So there's a huge literature now in ADS-CFT, and it depends very much on the level. So I'm going to mention a few. So one reference that I like very much is Maldacena Tassi lecture, 2003. So I'll use some topics. It's of course very cryptic. It's very short, but it has the key ideas, and it's something that you definitely need to consult. I'm also using a book by Amon and Erlinger. So this is a recent book. It contains a lot of information, a lot of background material that is needed in ADS-CFT. And so there are other important references, but I think I'll try to just talk about those as they come along. So there's a note, or a set of notes by Alfonso Ramayo. So this is just a few of the references. They are very general, and I do recommend that you take a look. Some of them are more concise. Some do work out some examples, but if you want to learn this material, that would be a good starting point. There are many more reviews. There's another review that should go here, which is called Magu. Which is Maldacena, Haroni, Gubser, Oguri, and Oz. That's also very extensive. It contains a lot of material about ADS-CFT. So that's really a good place to start. Okay. So, but also we are in the school. So if you have any question about whatever it is, don't hesitate to ask me. I'll do my best. Or maybe I cannot answer, but I do my best. Okay, so I'm planning, so this is the plan for now, but again, this is all, this will probably change a lot. But I'm planning to have 2 lectures which are going to be introduction, sort of derivations, so let's say introduction 1, introduction 2. And then I'm going to go into applications. So the first type of application I'll be considering is finite temperature. And then I will discuss one of my favorite topics, which is Wilson loops. Wilson loops in ADS-CFT. So maybe I do less finite temperature, more Wilson loops, but that's roughly the 2 topics I want to discuss. Okay, so let me roughly, I have to start somewhere, so let's start with a solid statement of the ADS-CFT correspondence. And then so my approach will be a little bit circular. So I say something, then we try to think about it, then we go back do some little calculations. So it's again. So the main correspondence that we want to talk about is some relationship between type 2B superstrings in ADS 5 versus 5. With n units, have to have n units of flux. Of course, on this side is n equals 4 super young mils with group SUN. Okay. So let me write the coupling here in mils. So we're talking about strings. So yes. This string is I will talk a little bit more about these spaces. I understand that this might not be completed. So let me calibrate a little bit. As I said, I will need a lot of feedback to get it in the right direction. So how many people are familiar with this? Have heard this about this? Okay, good. How many people have never heard about this relationship? Okay, so thank you. Okay, so this is sort of the goal of today. Try to convince you that this is true. Try to convince you that this is true. But again, if you have followed the courses carefully, the convincing is one page in Clifford's book. So all as Clifford was saying yesterday, all the hard work you have already done. I just have to point in the right line. But anyway, so we want to study a relationship between these two theories. And the first thing that I want to talk about briefly is about regimes. So here I have two numbers. So let me write them together. Here I have yes, and I have so the unit of flux. Yesterday, Clifford explained that if something has Ramon charge, it has to have some number n of that charge, just because of the Dirac quantization condition. So I can think of the flux, but the flux will be related to the length of the space, so I can think of some length in the string unit, so I'm going to write it like this. Okay. And now what we need to understand, or what the proof or the argument about ADS-CFT will roughly concentrate is when these parameters are going to give me a good description of the theory. Okay, so that's essentially the story. So I will let me draw a few more pictures. As I said, first I give you some idea. So this is where I want to go. I want to convince you that this is true. I'm going to mention some of the ingredients, and then I'm going to try to write down exactly what's going on. Okay. So what I'm going to argue is that something that you also heard is that D-branes have at least two descriptions or two regimes in which they are described by better in one using one tool or another. So if you're considering one D-brane, one D-brane in space, so this one you more or less agree that this is going to be described by open string ending on it. So this is not a fixed, so this is a dynamical hyperplane. It can fluctuate, and we will describe very carefully the fluctuations of that object. But the key thing is that there is a regime. We will be much more precise about that. There is a regime in which D-branes are really best described by D-branes by open string ending on some hyperplane. So we can very quickly try to understand what is the logical thing to do here. So one logical thing is, of course, whenever you're talking about the string theory, so in this case would be open string, so let me write it like this. So this has to be very small, so we don't have to deal with higher orders in perturbation theory of the string, etc. So we definitely want that. And then one thing that can happen, and that also was discussed several times, is that you would like to have some effective theory. So that was some question that was discussed yesterday, but this is a very crucial concept whenever you want to isolate some kind of degrees of freedom. And there are many ways to discuss this, but this is a very important thing. So one thing, yes.
Can you write a little bit bigger?
Yes.
Thank you.
I can write a little bit bigger. Thank you.
A little bit much bigger.
Okay, good. So this is E for energy. And so now again, to wake up, I need to ask questions, I need to get interaction. So if I want to focus on some ranges of energies in this theory, what would be a natural set of energies that I would like to focus? This is a question. So I want an effective theory of a string, so Clifford yesterday wrote something, but that should be in a regime where the only degrees of freedom that are allowed are, let's say, the lowest, no, the massless. So what is it that I have to take out of my spectrum? Massive. So anything that has energy of the order of a string, so let me write it like this. So let me write it like this, LS minus 1. So I want energies to be a lot lower than the first sort of string states that can appear. So that is something that is very logical to do. And this is essentially, again, more or less the clue to discussing this description. There's another description for the strings. And in that case, we have, which was the second part of I think, of Clifford's path. So if I have many deep brains, so they will, I'm going to write it like this, but this is, of course, so can this be, is this more or less clear?
Yes.
Yes? Who said yes? Okay, what does it mean?
We had a couple of many deep brains.
Yes. So we have many deep brains, and then I just try to say that they're so heavy that they change space-time. So my changing of space-time is some kind of curve like this, and then maybe there's flat space around it. So then, of course, in this picture, I also will have so in this picture, it's much better to have. So here I can have, of course, closed string living here. I can still have some open strings. But the key thing is that the best description for this object will probably be in this limit, when I have a heavy stack of deep brains, is going to be some gravitational description. Oh, sorry. I'm writing. So let's call this the gravity picture. And this, by analogy, would be the field theory picture. Okay? So now what we need to do is to find, okay, go to, all I'm saying here is words. But what we need to do, we know an equation for this description. Does anybody remember the equation that describes a string in this regime?
The action?
Yes.
Super Young-Mills.
Sorry?
Super Young-Mills.
Super young Mills is already a limit, but Clifford wrote some Dirac Bonifel action. I will write it also, but I just want again. First, I want. So there's an action that describes the system at very low energies, right? It contains also the fluctuations. It gives you Young-Mills. Eventually, this is what we will find, that this in the appropriate limit will give me Young-Mills. And here I just have 10-dimensional gravity. Okay, the 10-dimensional gravity that appears as a result of having n deep brains in my background is the description that is most appropriate in this regime. And what I have to convince you is that in appropriate limit, I will get a string on ADS5 plus S5. Okay. So now this is the cartoon, if you wish, the roadmap. So now in the next, I think, 10-15 minutes, we will do this in full detail. But this is, again, this is the closest we can get right now to a proof of ADS-CFT, to arguing that these two sides are the same. Okay, any questions?
Here in this gravity picture, how many dimension is gonna be the gravity.
Good. The gravity is going to be in 10 dimensions.
Okay.
Okay. So let's see. Now again, this is, if you're not happy with the picture, then we will have formulas. But I just want to tell you where we're going. If I started this lecture writing Dirac-Borifo, taking a limit, then you might not know why I was doing that. Now it's clear what I'm going to do. Yes.
And the interaction will be between low energy modes.
Low energy modes, yes.
What's special about the ABS1?
Good. So it's okay. So that one I need. Okay. So the answer is roughly is that the strings, the description of this part, if you wish, is going to be described by ADS5 process 5, and then there's another piece that that we hope it decouples, so we will argue that it decouples, and that's what is special. That ADS5 process 5 is indeed the geometry that create that brains create. That's what's special. Okay, so good. So so let's write one formula. And what I'm going to write is the Dirac-Borifo action. So Clifford actually did a much better job yesterday. He also wrote, there's another piece which is the Wessumino piece. It is important, but not super important right now. So I'm just going to write something like this. So remember, a D brane, in this case we're talking about D3 branes. So this is an object that has a four-dimensional work volume. So we can write it like this, and the action minus determinant of pullback of the metric plus 5. So do you remember this from yesterday? Sorry? Okay. I probably should not use pullback because Clifford yesterday used so unkindly words for pullback. So let me, so you can think of this as the induced metric. So I'm going to write it. So G, A, B. Now my A and B are four-dimensional indices, so they go 1, 2, or 0, 1, 2, 3. So let's have 0, 1, 2, 3. Okay, and so this is an object that was, so here's what I want to construct. Okay, so this is the 10-dimensional metric, and I'm pulling back to some 4-dimensional subspace. So that's, instead of writing all this, sometimes people write just this, P, which is pullback of that metric. It's a more general. Any other question about this? This F is about. Okay. So I'm not including it right now. I could put it here. Sometimes, okay. So sometimes people use this curly F that contains Chi Ramon and also contains the field strength of the gauge fields. But I'm not going to do right now. Yes.
The indices nu and nu go from 0 to 9.
0 to 9, yes.
How can I get the determinant of the matrix, which is 4 by 10?
No, it's not 4 by 10.
No.
So this is contracted, so it has no index in the spectrum. It only has 4 by 4.
4 by 4, yeah.
Okay.
Yes.
In fact, okay. So let's disentangle this a little bit more so that we are so mu and nu are from 0 to 9. Okay. So let's also be a little bit more explicit about the fields that are involved here. So there is a gauge field, right? So HA in the work volume of the brain. This you already saw in the spectrum of a D3 brain as psi minus 1/2 acting on the vacuum, right? Okay. Then there are other fields that I'm going to call sorry. So there were okay. So let me tell you what. So you should remember this. This was 1 to 6. So these were the gauge fields, the fields living on the brain, correct? So the gauge field on the brain and the transverse directions. Right?
Yes.
Okay. So let's see where these are here. So here I have been, this part is a little bit too general, but what I'm going to do is, of course, well, not of course, but I'm going to use something akin to static gauge. And in this case, essentially all I need to specify are the fields leaving. So this xn will be this, and then these are the rest. Okay, so these are fields that will be transferred to this. So the ones along the brain are going to be fixed to be the work volume. Okay, and then the fields that you discussed yesterday, this is very physical, right? So this is, in a sense, we have a the brain, and then we have these transfer fields that determine the transfer direction. So these are going to be these 6 in 10 dimension. I need 6. So these are these 6 fields. These 5 up to 2 pi alpha prime, etc. are the same. Which I will not write. Okay, so now what we need to do is to, okay, so I was a little bit, so this is the key aspect, but let me be a little bit more complete. So this system, or the low energy degrees of freedom of this system, if you think of trying to write again, the key idea is always this notion of low energy degrees of freedom. So if I try to write the low energy degrees of freedom for this system, in this regime, what I have is, so this excitation of the brain, Dirac one info, which I just wrote. Then I will have, I can also have some closed strings. And then I have some interaction. That's more generally the low energy effective action of this system. Now my focus, of course, has been on this object, and this is what I try to spell out there. And there is where I'm going to be more careful about taking the limit. But these 2 terms are still there, and we need to deal with them appropriately. Okay, so the part that corresponds to X close, let me write it once. Maybe I ask somebody to let me know, somebody can tell me what this part would be. What are the effective action of the low energy degrees of freedom corresponding to closed string? Exactly. So this would be some 10-dimensional gravity. So just again to more or less introduce notation, I'm going to do this. Okay, I will not write, but well, maybe I write one just to. Okay. So then there is interaction between open and closed strings. Those terms will come, most of them will come from here. And you can see, for example, the dilaton, which is a closed string mode, will interact with open string degrees of freedom here, with this and with 5, etc. Okay, so now, so what I need to do now to connect to n equal 4, one important step is now I need to expand this action in the regime that I'm interested. And the regime is, of course, very low energy. So I have to consider, so for the metric, I hope this is somehow familiar. So this would be flat plus kappa fluctuations. And I'm going to expand. I'm going to expand everywhere. I'm going to expand this. So there's one formula that you might have not seen. So Clifford asks you this to expand this as a hardware around flat space. I don't know how many of you have already done that homework. But there's really one formula that is crucial. So I write the key formula that one uses, and then I'm just going to plug the different pieces and get the answer. So the key formula is essentially something like this. So this one, if you have done GR, you know how to expand something like this. Determinant, square root of the determinant of the matrix, which is what is here, right? So I have this matrix plus my gauge field, and what I need to do is to expand it around some constant matrix. Okay, the answer here is essentially, so I'm going to define this, but so let me define an object that is going to be M. So I can do this in more detail, but again, I don't think I want to spend a lot of time. So this metric will have well, this is for the metric, but for most of the field, there is some background and then some fluctuations. So what I'm thinking about is to have this metric modified by some fluctuation. So the background will be some number. It will be determinant of 1, right? And then I will have all other little pieces. So what this formula tells me is how these little pieces come in. And so I'm going to write it like this. It's determinant of the metric. And then there will be 1 plus trace of x plus trace of x square, and then I have another trace another higher order term. So that's the key thing. That's the key identity, if you wish, and you can obtain it in different ways using the real different. Okay, so let me write the answer. The answer for this would be -1 by yes. So let me stay with my indices. So that, I don't know if it has been written before, but that is, just 1 second, that is the effective function of the open string degrees of freedom that live from the Libre in this link. Yes?
It's the same, but
that part, determinant of n,
Yes.
it's equal to determinant of n.
Okay, so, sorry. Let me do it carefully. N plus some delta n equals like this. Okay? My delta n is going to be, like for example, FAB is a fluctuation, so there will be a small little, I mean, I don't want to be too loose, but I also don't want to be too technical. In the sense that if FAB is small, so it's not, you have to have some measure in the space of matrices to tell that it's small, but for this problem, you don't need to be that complicated, so you expand this, and that's the leading terms. Okay. So how many people have seen this in any of the lectures? Something like the low energy degrees of freedom for the D3 blend. Wow.
I have a question.
Yes.
Why did you start with the action of the closed string and
Where is the action of the closed string? This?
there? Yes.
Okay, so
and you finish with the open string.
okay, good. So let me go back here. This is the system I want to describe. This system contains two pieces. Let's say the open string degrees of freedom that live here. There are many other degrees of freedom. They're all like closed strings somewhere else. Right? This is type 2, 0. So those are also here, and then my also interact. Okay. Now I want to take some low energy limits, so I want to consider only states that live in this regime, or if you wish, I can say alpha prime goes to 0, but that's a little bit less careful. Okay. In that limit, this piece is here. I have not said exactly what it is, but when I take the limit, I will essentially have type to be closed string in flat space. Okay, this is what you have before, that you have been studying out. The part that I spent some time working out was this part, the open, that contained this Dirac Bonifil, and that gave me n equal 4. Okay, good. So this part is there. I cannot just take it away. But what I am arguing is that interactions. I'm sorry that I have too many files. So let me go this one. So interactions come sub-limit. So to a very good approximation in the limit that I'm studying, very low energies, when this description is correct, my system reduces to two pieces that don't really talk to each other much. One is just closed string in 10 dimensions, as we usually have, and the other part is okay. So here I have talked about the boson part, but this is an n equal 4 abelian multiple. So. Okay, that's what I have shown. So any question about this? Is this clear?
Where is the dilaton?
Where's the dilaton? So the dilaton I also expand to something that, let me call it phi 0, and then something that was also kappa phi small, and it does not appear there. The only thing that appeared was phi 0, which I sort of renamed GS.
So you have phi 1 to 6 and phi 0.
Sorry, no. Phi 0 is let me do this. Completely separate thing.
So is this open action the limit when you expand this dBi action, isn't it?
That's the leading part when I expand. There are other pieces that they are proportional to alpha prime, which I take into 0. So in the strict limit of alpha prime goes to 0, there's, for example, there would be, I didn't write it here, but this is only the quadratic piece. There will be trace x to the 4th, and that would be some f to the 4th term. But that would come necessarily with alpha prime, so I don't want to write it. Is it?
Yes. Sorry. F is the field strength of the sheet A fields.
Yes.
Okay.
Of the sheet, what sheet?
She or she, I don't know what the wait, A. Because you wrote there x mu equals, what's that?
So this was the 10-dimensional x, and the 10-dimensional x had some part that I identified with the space-time. This is called static gauge. And the other part are going is in general is connected to these fields that I also knew from studying the spectrum of these 3 planes. Yes.
So, only to know, to be clear for me, what you call field theory is the low energy limit of type 1 superstring?
The low energy limit of the, yes, the low energy limit of this degrees of freedom here, open
Because
string,
type
with
1
this boundary condition.
The LASS2015 is the interaction between the closed
Open and closed, yes. So a lot of those are already incorporated here. As I said, closed string, the dilaton, will interact with open strings, and also through the pullback with this. Okay. But again, in this limit, they will die off because it's a hard pullback.
And this data you reabsorb in the constant.
Yes, yes.
The theory is already conformal.
Say that again.
The theory is already conformal with these actions, or no, you have to do some new. Because you are in the field theory side, the correspondence is CFT.
Yes. The n equal 4 is a conformal theory. But that I have to argue. Okay. So good. So we have seen this. So now let's focus a little bit on the gravity side. The gravity side. So let me have let's close. Which was essentially 10D strings in flat space. So now what I need to do is to go to the other picture and see what is going on. So this is here. So there's, as I guess also was discussed, so I want to now write the background that is generated by ND3 branes. So this contains a metric, and in this case it will contain a C4. Okay? So I'm going to write it. So this is H minus 1/2. Okay, this mu is 0, 1, 3. 0, 3. Then I have square. So let me go like this, dr squared plus I squared. This is the phi sphere. Okay. This is the radius in this 6-dimensional space perpendicular to the plane where the brane is. So you can see there's Poincare invariant in this plane. So C4 is going to be 1 minus H 1 dx0 dx1. Good. So the dilaton is a constant. So H, does anybody remember or know?
1 minus
1 what? 1 plus? R. Okay, let me call it L so that I don't mess up. L to the 4 divided by R to the 4. Now, because this is a background that corresponds to strings, and because, this is a background that corresponds to some D branes, and because the D branes are quantized, when I can compute the charge of the D-brane, looking at the phi form that comes from here. And that essentially tells me that at this point, this is an arbitrary constant, right? In this solution. But this constant has to satisfy the quantization condition. Anything that has D-brane charge has to come in some integer number of that D-brane charge. So that quantization condition with all the powers essentially turn into this expression. Okay? So far so good? So now I'm going to do something. So now I'm going to do something slightly different. What I'm going to do is I want to consider this is a solution, right? This is some space, it's curved, etc. It has again flux. I'm going to now consider two regions. So one region would be R a lot greater than L, and the other region would be R a lot less than L. So what happens when R is a lot greater than L? What goes to
We
0?
could approximate H to 1.
Then you can approximate L to 1. So H is approximately 1, and then my space is essentially the dimensional flat space. If you wish, so if the branes are equal 0, so very, very far away from the branes, the space looks completely flat. That makes sense. Now, when R is very close to L, so what happens is, of course, this term dominates. Okay? So these terms dominate. So let me write, I'm going to write only, so I'm going to only write the metric here. So what happens to the metric? So again, H becomes L squared divided by R to the 4. So essentially I have R squared divided by L squared, eta mu, dx mu, plus L squared over R squared dr squared, plus L squared d omega phi. So this space, I will discuss in more detail, but this is a product space, so I have a phi sphere, it's on radius, and this part is called ADS phi. We will discuss that. So the space becomes ADS phi. Francis. But this was just numerology. So now we need to see what is the physics inside that can allow us to understand these two regions as separate regions. If they can indeed be separate. Yes.
Can you repeat how you get these electrical equation? Because it's giving me the relationship between parameters in both pictures.
No. I'm talking, all my talk here is all gravity. This equation, okay, so there was a condition that I haven't written, but so from this S5, from this C4, you can construct F5 by P on this, right? This is like the field strength in electromagnetism, if you wish. So now if you want to compute the charge, you have to integrate this. This you will integrate over S5. And that will tell you the charge that is inside. But we know that what is inside has to be related to the branes, so it has to come as an integer number. So there's some normalization in the integration here, and that is the outcome. So again, for gravity, this is a perfectly good solution for any L. But then the brane quantization tells me that this L cannot be anything because it comes here related to the charge of the brane. So it has to be a multiple of that single charge that Clifford discussed yesterday.
Sorry.
Yes.
GS squared goes with the exponential of the dilaton. We are taking some particular value of the dilaton
Where?
in order to L be constant.
So this is a constant.
Yes.
You mean?
Therefore, we are taking the depth, for instance, of the graviton, but the dilaton.
So the dilaton in this solution is some constant.
That's it.
So this is what I do. Okay, so now we can go to try to discuss this picture a little bit more. So if I have some close string here, okay, so let's discuss what happened to states that want to live around this R very small. Okay. So let me again go back to my map. So in my map, as you saw what I did with the open string, with the deep brain open string part, I convinced you that the dynamics sort of separates into two pieces, one that corresponds to n equals 4 and the other one that is 10-dimensional strings. Okay. In this picture, roughly what we see is that far away from the stack of the brains, what we have is roughly what would be 10-dimensional strings in flat space. And then my question is near, so I will have something left close to the deep brains, if you wish. And now what I need to argue is that these two sectors are fairly separate. They cannot easily talk to each other. That would be the part analogous to saying that that the interaction also vanished in the alpha prime goes to 0 ring. Okay. So if I have so let me consider some excited state. So let's call this region the throat. Okay, and now I'm going to talk about this region. So if I have some state, so if I have some state in that region, so let's assume that it has some energy ER, and we can consider that energy in string units. Okay. Well, first of all, there's okay. So let me first make this argument, but there's already a GR argument. There's already a GR argument that I could make for the separation of these two parts, but I'll let me first discuss this one. So because of the redshift, this part here, so you see there's some, let's say there's some energy that I can define in this frame, and then there's like, let's say like the bulk or the circular energy which will contain this factor. Okay? So this is what I'm, if you wish, more GR thing is like the redshift factor, right? That you write the square root of G00. So G00 is R squared over L. When R is very small, this is a highly redshifted situation, right? Is that clear? So in GR, right? In GR, when you're getting close to a horizon, you see that there's redshifting. That's roughly because if you look at the energy of some quanta as seen from very far away, you have to multiply by the square root of G00, and that's going to 0. So it makes it very, very small. So it's the same effect. But here, there's of course not really, there's no horizon. It's just the throat, that region where there's some physics, and that physics seems to be very decoupled from the physics outside. Okay? So it's the same physics. It's the physics of of redshift. So what I'm going to do is just to write it. So the energy seen from an observer at infinity would be something like this, V0, 0. The energy of these string modes that wants to live in there. And now you can see, oh, so let's write, because this object, this was like R over L. If I want, I can write it like this, so let me write it like this. This will go to 0 in the alpha prime for R over L very small. This goes to 0, so the energy of these states can be very small. So there are two, and this is the main sort of the key punchline. So there are two kinds of very low energy modes that we have in this theory. So one are the standard modes that you see in 10D gravity, but there's a new set of low energy modes that appear precisely due to this redshift factor. So this is now more or less the punchline. So this gravitational description also split into sectors. One sector is this, which is essentially a string in flat space, and the other sector is strings that live in this ADS5 process file, which is in itself a solution of type 2B supergravity, but in this language we are viewing it as a region of the deep brain solution.
So R is a coordinate.
R is a coordinate.
When you take it very big, it's intuitive to be in a flat space because you're taking at least,
yes.
No. Yeah, one coordinate it's intuitive, the other one are in spherical coordinates. So L is a constant?
L is a constant, yes. So that is essentially, so let me write it. So we have two sectors of low energy modes. So one was to be on ADS5 process 5. And then we have to be in flat space, which is these other modes. Now, what I have discussed are two descriptions of the same object in different regimes, but the same description of the same object. So now if there's some consistency in this story, it is natural, okay? It's not a proof, but it's natural to conjecture that therefore this part, so this part should be equal really to what was left, to that sector of n equal 4 gamma. So that is n equal 4. So this is the conjecture, okay? So there's some sectors, there's some limit in which the sectors decouple, and what is left that is non-trivial are these two pieces. And then we conjecture that they are, of course, the same description or different description of the same physics. That's the Maldacena conjecture.
Question?
Yes.
So
now, yeah, so now we have gone, as I said, I work, I will be I will work in circles. So the first circle was to draw pictures of what I was going to do. Now I took the limits in the appropriate equations, and the key is that in both of the cases there were two sectors, and they decoupled, and then now it's natural to conjecture that the one that is different is in fact the same. Okay? That's the Maldacena conjecture. So now we can discuss. Yes?
What do you mean by the same?
Okay, so the D3 grain is one object.
Yes.
I describe it in some regime using some physics, okay, of open strings, etc.
Yes.
In some other, I have another description in which I describe it with gravitational fields. Now, in that description, in the limit of flow energy, there was a splitting. So, in particular, in the deep brain description, there was one sector of my low energy modes completely described by n equals 4 super young mills, and the other low energy modes are described by type 2B string theory in 10 dimensions. Okay, that's what happened there. Then I went to the closest to the gravity description, and I found that also this description splits in two pieces. So one piece very far away, if you wish, in this language. So now, because, okay, so very far away, and what I see very far away is the same. So this thing is the same as this one. Okay, so I am accounting for the low energy modes, and the description is the same. So what is the part that is non-trivial? The non-trivial thing is that something that contains field theory has to be, if they are describing the same thing, equal to something that is intrinsic like gravitational.
But what does equals mean? For example, if I calculate something.
Good. That question is for tomorrow, or for later today. No, because that's a very good question. That's the key question, right? It doesn't buy me anything just to say it, right? I need to turn it into a machine that works, that computes things. That's what we will do. Okay, that's what that we will do. So in particular in the CFT, all the information is in correlators. So I need to learn how to compute correlation functions using gravity. That's what I will do. Okay? And more interestingly, and this is really why this subject is so fascinating, now there are questions here about black hole physics and paradox, things that people don't know how to solve here, and maybe if we translate it to something in field theory, then maybe we have a chance. Okay, so now this becomes a very powerful tool indeed. Yes?
And the gravity side, you had like n the brain, the three brains.
Yes.
But in the field side, you were just describing one brain. Right?
Thank you very much, indeed. So now if I put many deep brains, and that was an exercise that Clifford did. So I have, right, so this is, so I describe it one deep brain because it's easy. But suppose I have two, and this is what Clifford was saying. I have this brain, sorry, this string, and now I have bi-fundamental string, if you wish, or bi-strings that go from one to one and the other. But when they are on top of each other, this of course enhances to a non-abelian. So when I have n brains in this picture, what I need to do here is to write trace and allow these guys to be in the UN adjoint representation.
So in those descriptions you have n brains?
Yes. I started with one because, why I started with one? Because if I want to start with n, then I have to answer what is the non-abelian Dirac-Bonifel action, and nobody really knows what that is. Okay, it's a very messy object.
But when you put there a lot of brains, they are gonna deform space-time.
Good. So I have to be. I gave you at the beginning. I gave you some idea of regimes in which descriptions are going to be good. Now I can return to that. But I'll have to be in the regime. I can have n large, but I have to have ns very, very small, and that still is going to be a good description. Okay. Good. So let me again let me now say a few. Let me make some remarks. Yes. Okay. Okay. So let's now talk a little bit about this. So let's do some remarks. So hopefully I convince you because I have a powerful tool behind, which was the brain technology, right? So that's why it was really, really crucial that I understood the brains, I understood their properties. I knew that they had Ramon charge, and that they were the quantum of Ramon charge. So anything that contains that charge has to be a multiple of that. So I use a lot of the brain technology, and that makes this argument very plausible. Okay, but I have to make the following remark, which is already in Maldaceno's original paper, which of course I recommend that you read, because all these arguments of decoupling are subtle, so you need to read them until you become very comfortable. But in that paper, if you go to the paper, essentially, so you can think of this. So what we did for the DC brain was, again, alpha prime goes to 0, and there was some length, which was R, so actually some energy that we kept fixed. So you can see that this is equivalent to what I was saying. Essentially, if I write, so let me write this. It would be, so let me write this just so that you know the way that the Senna did it, because it also teaches you something. Okay, so we have this. Now I'm going to rewrite this as 4 pi gs n alpha prime square over r to the 4. And okay. So if I want to write this in terms of u, so if I want to write this in terms of u, I have to write 4 here and 1 to alpha prime square here. So this would be u. This I want to keep fixing my limit. So when I take alpha prime goes to 0, this, of course, this 1 would be dropped out, and I just take this term. So everything that we said is the same. It's just that this is a different way to view it. The powerful thing about that is that, and this Maldacena did in his paper, is that now I have other solutions. I can run the same argument for an M2 gravity solution. I don't have an M2, I don't have membrane technology. I don't have the open string, the open membrane language, okay? So this is telling you that now we're moving, so the ADS-CFT moves into less, let's say, solid territory, but in this language, what I need to do is to take, so what is the right scale here to take to 0 for them to brain? Okay, so this is not a theory of a string, this is, we take just m Planck to 0, and then we keep some u squared, which is r divided by a Planck cube fixed. And this will give me, is correct, sorry, this is for the M5 brain. For the M2 brain, I'll do similar, m Planck to 0, and u 1/2, which is r over m Planck 3/2. So if I do this substitution now, again, without the power of deep brain technology, but nevertheless, I can also try to argue that there are two sectors that decouple. So the main brain, the M5 solution, essentially becomes ADS7 process 4, and this one becomes ADS4 process 7. Okay? So these are, again, I want to make that clarification. They are not in the same footing as the D3 brain duality that we very carefully were able to chase through its different forms, because we knew how to describe the brains microscopically. But here, if you're brave, you can say, okay, the fact that there's also this decoupling that I talked about between stays close to the brain and stay far away to the brain. And this, so the claim is that this would be dual to some conformal field theories. Again, you might not be completely happy, but I mentioned this because so this is a big subject, the ADS-CFT, and there are some approaches that are less stringy rooted. So a lot of times people take some ideas, like for example, if I have some metric or some gravity backgrounds in which there's a limit in which I have a space of this type, then it's probably telling me that there might be some duality. This is less, as I said, less solid, but worth mentioning.
Why do you need to introduce membranes?
Sorry?
Why do you need to introduce membranes?
Okay, so this, I was looking at some supergravity solutions. In this case, in fact, there are all the papers in which people did this for any DP brain. But then it is more subtle because the theories are not conformal.
Why you write it like M5, M2?
What
Does it, those cannot
Okay, sorry. Good. So DP brains were solitonic solutions of type 2b, type 2a. Okay. 11-dimensional supergravity also has solitonic solutions, and they are co-membrane, M5 and M2. So
But what does mean 5 to 2?
Okay, so what does 3 mean? 3, you should know what it means.
Yes, I know. But
What does it mean?
3 because of the Dirichlet conditions.
Because of?
The number of Dirichlet conditions.
Good, okay. Good, in this case I don't have that language, I'm just using this language. So a D3 brain will couple to this F5, okay? So 11-dimensional supergravity contains an F4, and it can couple to a membrane, or the dual can couple to an M5. So it's at the level of supergravity, just purely supergravity. There's no stringy description of these subjects, okay? I'm mentioning this because when you go out to the world, you will see many papers about LASS2015, and probably the majority these days are about this part, for example. Okay, so the first thing that Montesena did, and that I think we should also do, of course, is to argue that this is not obviously wrong. So that's whenever you have a conjecture. So usually people in mathematics, they make conjecture because they check many cases and then they can find a counterexample, so they think, okay, this might be true. So this is more or less the same reasoning. So we have to make sure that certain things are not, certain things have to match, and the simplest thing to look at are symmetries. So symmetries, of course, they are crucial. Yes?
So a little question. When you obtain S open, you expand around a flat metric.
Yes.
It's okay. But I suppose that it is so far away from the brains. Because how can you expand around a flat metric near the brains? Or maybe I've lost.
No. I mean, these are two descriptions. So in gravity, I'm looking for some source, an object that is heavy, and will change the space-time. So that's what I look. Changing space-time means I need to find what is the metric, how is the space now behaving. So in this case, I start with 1D brane. So this will not change the space-time. The space-time is still mostly flat. And that's what I'm looking at. What is the dynamic of this thing in that regime?
So it's not the same system you studied in the gravity side?
It is the same system in a regime where I can describe it using this language.
Why are you allowed to describe in this language if you have any memory?
Okay.
I think you first consider the interaction. The GS is small at the beginning, and then you consider low energy, and you get super Young Mills. And then you go to strong coupling, you get Young Mills at strong coupling.
No, this Young Mill is not strong coupling.
Not yet. Okay. But at the beginning, when you have any D3 branes, you consider GS small. So the
GS is always small here.
Okay.
So I will.
Even though you have a lot of D3 branes, if GS is small, their gravitational fringe will be small.
Right. So this one we can I can.
So you can consider flat space. I mean, this is the point.
No, it's not because you use static gauge in the static gauge and just metric in the world volume becomes the space.
No. This static gauge is not the key thing.
There would be some explanation why we're allowed to use flat space there.
So what space do you want to use?
No, I mean, when you have many branes, those deform space-time.
Not always.
Those deform space-time? Yeah, of course they do. But this is my calculation. So they deform space-time, but I'm taking. So I took alpha prime to 0, but kappa contains alpha prime like this. So gravity is also going to 0 in this limit, right? This is what I explained in taking the limit. Okay. So the kappa is the gravitational coupling, right?
Okay.
So I did this consistently in the whole system, okay, and that's why it became self-leading. In fact, I could have, I did like this, right? This is the standard perturbation expansion, but this one I took flat space, but I could take in principle any fixed background. But the key thing is that it will be fixed, because then corrections will come with alpha prime to higher powers.
So what allows you to pick one of these are conditions of alpha prime, limits of alpha prime.
What allows me to?
To go from.
So I can view it as, I mean, so it's the decoupling that I was talking about. I want to make sure that all stringy states go away of my spectrum, so I can have an effective theory only for the lowest lying excitation. Okay, so what are the symmetries? So n equals 4 is a conformal theory. So the symmetries are, so conformal means beta function equals 0. It's a little better like that. So it has in fact a whole conformal group, which is a 4, 2. Okay. Then I will not talk about supersymmetries, but of course it has it is supersymmetric. Yeah, I guess I have to talk a little bit about supersymmetry. So the supersymmetries is n equals 4, so they are rotating with SU4. So SU4 is isomorphic to SO6. So maybe I can do this a little quicker. Good. So now I have to find where the symmetries are in ADS5 plus S5. So these are precisely the symmetries, isometries of S5, SO6. And then, so then I have to convince you that the symmetries of ADS5s are this. I don't think I can convince you very easily, but let me give you one definition of ADS5. Definition. ADS5 is the hyperplane given by some equation like this. So this is the hyperboloid. This is one of the definition of ADS5. You can see that this equation, of course, has the symmetries. So this doesn't do anything to ADS5. If you are interested, if you are gravity-minded, I recommend that you look at the Killing vectors of the metrics that I have written and show that they are indeed in this algebra. Okay. But this should be enough. So at least at this point we agree that the symmetries are the same. So that
why was SO42 a symmetry for the conformal group? Is that the conformal group is isomorphic?
The conformal group in 4 dimensions. Okay.
What about the S5 piece?
The S5 piece,
That also has.
the isometry of S5 is SO6.
Oh.
Okay, so I have now. Okay, I have 10 minutes, I guess, and a lot of things to talk about. Okay, so let me make one comment. This is an extra remark that I want to make. Okay, because so one of my agenda, one of the points in my agenda is to convince you that even though the way that we can argue this duality is in the right place to argue it is the discrete brane, this seems to be much more generic than we think. Okay, so that's, I want to give you some argument. This is not proof. This is just an argument that this might not. I mean, this is not completely wrong. So the first argument that I want to give you is due to Hoff. This is 1974. And so the question is again along this idea: how general is this thing? Okay, so we know there's some context in which we can track all the degrees of freedom, and we can track what they become in certain limit. And in that limit, we see that a gravity theory. This is very amazing, right? A gravity theory is equal to a field theory with no gravity. But of course, there were many predecessors, many precursors to this idea. This idea has been appearing often in the history of physics. So this is one of his phases. I want to discuss that with you now. But there are many other ways. Okay, for example, I can talk about that in the question session. But the way that string theory was originally discussed was because of this, because there is a connection between field theory and gravity. But anyway, so what Huff was saying, he was interested in considering, he was interested in considering SUN theories, so with some gauge field. And so here, of course, he wanted to consider these theories with some coupling, with this number get fixed, and then n goes to infinity. Okay, and what he argued, and we will argue, it's half a minute. The argument is that this is a string theory in this limit. Okay, even for SUN. But it's a very special limit. So let's see, the argument goes as follows. So suppose, and you can see the power of the argument, why ADS-CFT or gauge gravity should, in principle, somehow be very fundamental. So let's, okay, so this is, I'm going to slightly modify the argument of Huff, but nevertheless, here's the idea. So suppose I have a theory of matrices, okay? I can have m squared, blah, blah, blah. I can have anything. So let me take it to be simple, some potential, okay? But I can have, so let's see, m squared. I can have any vertex. So in any theory, so M is of course, I have to tell you, M is a matrix. M is a matrix. So I want to study the, or let me go back here. So let's study the perturbation theory of that theory. So again, I want to emphasize that this is very general. All I need is that the theory has some matrix structure like that. So then, so here's, because M is a matrix, I'm going to use this double line notation. If you have never heard about this, it doesn't matter, right? The key thing is that I have some Lagrangian, and I can construct my Feynman rules, and then I can construct diagrams. And what I'm going to do is just some counting of diagrams. It's very, okay? So for example, I can have cubic vertices, or quartic vertices. This. Okay, so these are vertices. Okay, so now let's count. So a propagator, each propagator contains a power of g squared. So you look you look at the form, and the propagator comes with 1 over g squared. Any vertex comes with, what is the coefficient for any vertex? Sorry? 1 over g squared. Right? This is what accompanies whatever vertex is there. So now let's do Feynman diagram. So let's do, for example, this. Okay. So now one more thing I need to tell you: if I have trace, it gives me a power of n. So these are my Feynman rules. This is the propagator. These are all vertices are like this, and each closed line. A closed line, of course, means to close this line, I have to say that I equals j, right? And that's like saying trace. And for this matrix, it gives me a power of n. Each closed line contains power of n. Okay, so good. So the claim is that this theory will organize itself in some sort of in a topological expansion. So let's see that. So an arbitrary diagram. Let me see what I can. So I don't know if I should do examples, or one example, or two examples, or I should write the formula. How many of you are somehow familiar with this or have seen this? Okay, so most people have not seen it. So let's do one example. So let's consider this diagram. Okay, let's consider some vacuum diagram, and then so let's compute. Let's see what this diagram has. So this diagram has how many closed loops? 3. Does everybody see 3? 1, 2, 3, the outside. No? So that means Feynman tells me NQ. How many propagators? 3 propagators. So that tells me G squared. Oh, sorry, G squared cube. And then it has 2 vertices, right? So 1 over G squared. So this I'm going to write as n squared G squared n. Okay. Now this, and I hope that you remembered your what is it called? Your high school topology. So this is so this is a planar diagram that I can draw a sphere. So it comes with n squared. And then this is left fixed in this Hoff limit. So G squared n is fixed, and n squared. So that means so let's see that this thing detects topology. Okay, so I will now make my statement, and then I will fill in blanks or details if you want. But essentially, for example, we can consider all the diagrams that cannot be drawn on. I mean that will have some crossing. And they will give me less powers of n. But the key idea, or the main idea is at the end I will have n squared, and then I have some, this will be 1 loop, 2 loops. Okay, but the key thing is that my diagrams are now going to organize themselves in a nice way. And so this, for the planar, this would be some function of G squared n. Okay? And now, in general, for the partition function, let me write it, and we can do one more example to convince you that we're doing the right thing. So the partition function, which is essentially what we're computing with these vacuum diagrams, is going to be a sum. H is the number of handles. And H n to the 2 minus 2h. For f for every genus, if you wish, I have to do it. But essentially, this is the answer that you will get. So here's one example for homework, for this one. We can do it later. So you can compare this one with this one. Okay, so this one is not planar. This one, you see, this one is crossing over the other one. So you can now do this as an exercise when we're having coffee, and convince that if this goes as n squared, this goes as what? N squared less, right? So it would be as n to the 0. So h equals 0 was the sphere, and this is now in a torus, 1, so it's n to the 0. So this is a diagram that goes as n to the 0, and this is that goes as n squared. Now, the powerful thing about this is that you see I didn't use a lot of complicated QCD or any, there are other issues about dynamics. But now, let me make a, so I can make the punchline of Huff, and then we can criticize Huff when we start. So the key thing is, the key observation is that only planar diagrams planar diagrams survive this off limit. Again, n goes to infinity, and G squared n is like fixed. So you see, G has to be very small because obviously to keep this a fixed number. But in this limit, the argument, again, there are many ways to argue this. So you can say now that when you take n to infinity, this looks like a triangulation of a sphere, and this would be like a triangulation of the torus. And at the end, if I have n really large, this will sort of fill in these two-dimensional solids. And at the end, I will really have, like in a string theory, a perturbative expansion in handles. Okay? But but you see, the string, the worldsheet appears here as Feynman diagrams. They generate this worldsheet. Okay. So the punchline of this piece is that there are many ideas around that were all pointing to the fact that field theories, a theory for matrices, for example, secretly contain indications that they might be described effectively, right, in some limit when n is very large, g squared n is fixed, but that they might be described by things that want to organize themselves as strings. Okay? And again, this was long time ago. And there are many other indications, okay? There are many other indications. I think I will stop now, but I will stop now. Thanks. Any questions?
What are the other indications that you write it down?
Okay.
Search
So good. So one thing that I like to quote as an indication is ON theories of vector models. So vector models. So let me write vector models. So these are other theories. Okay, they are not exactly strings, but they are much nice. They are nicer at large n. They can be completely solved at large n. I wanted to show one example, but I guess it's fine. And then, of course, there's the observation of Regge trajectories. So if you look at particles in accelerator, like a lot of hadrons, etc., the best description for their spectrum is by a string that spins. Right? So this mass and spin relation is an indication that something stringy must be driving this spectrum. And that was really the original idea as to why, that's how string theory came about, trying to explain all this. But this is a fact. If you look at these plots, you say, okay, the object that best fits this spectrum is a string. So there's something stringy about these strongly interacting particles. So these are for me the key items.
Although some also have noticed in this diagrammatic representation of matrix, could you explain for people what's the tree vertex in terms of n?
Yes. Okay, so that would be a term here that contains 3 n's. But it has to be right. So it's on the trace. So what you need to do. So what you need to do is to contract the index appropriately, like I1, I2, I3, etc. But it's just something with three matrices, and then quartic for matrices, etc. But it doesn't matter as long as I have it like this. I mean, of course, I can. Their version of this, by the way, their version of this Hoff story, I can add. I can try to add all the degrees of freedom, but then the picture is not so nice. You have boundaries, you have to modify, then you have all this, but roughly it can be expanded.
Can you have dynamical objects in this ADS correspondence?
In the ADS correspondence?
Yes, like a black hole. You can collapse a black hole in this.
Yes, you can collapse a black hole for sure.
But how do you control that?
Good. So I can the best I can give you a much better answer later, but roughly. So I wrote string theory in ADS5 process 5. I can now consider dynamics of all the modes of those modes in gravity, and I can allow them to collapse. This is just an Einstein theory, and I know the fields that are playing. So the key thing for me in this exercise today was to understand what are the players. So what are the fields that survive at this limit? But I have an action for then, I can study any dynamical process, yes. Okay, let's stand to the point of